Now what about this setup? Let's say we have, again, two well-diversified portfolios. They have certain exposures to the macro risk factor. Let's say it's the market portfolio. Asset A has a beta of 1.4. Asset B has a beta of 0.9. And they have, on top of that, deviations from the expected return implied by their macro factor exposures. B has a positive one, A has a negative one. Let's say the risk-free rate is 5%, and the macro factor, the market, has an expected return of 12%. What is the arbitrage trade here? Well, naively, we might say, well, let's just buy, again, the one that has a positive alpha, sell the one that has a negative alpha, and maybe that'll be good enough. Well, let's see what that would actually lead to. The expected return on the asset with the negative alpha, A, is, well, the risk-free rate of 0.05, plus the alpha of negative 0.01, plus its beta, times the market risk premium. The market risk premium is 12% in excess of the risk-free rate of 5%. And that gives you an expected return of 14.5%. What about the portfolio with the positive alpha? Well, that one's going to have the alpha of 2%, the risk-free rate of 5%, its beta of 0.9 times the market risk premium of 12% above the risk-free rate of 5%, expected return of 13.3%. So if we want to go long, sort of share for share, one share of the positive alpha portfolio, which is to say B, and short one share of the negative alpha portfolio, which is to say A, well, that would be 13.3 minus 14.5, or negative 1.20. That doesn't sound right? First of all, we're getting negative expected returns. We probably don't want that in our arbitrage trade. But also, this isn't even an arbitrage trade since we actually haven't eliminated our macro factor risk. Why haven't we? Well, remember, we go long one share of B, so our portfolio beta is going to be plus 0.9, and we go short one share of A, so our portfolio beta is also going to be minus 1. I think it's actually 1.4 in the prior slide, but 1.4 or 1.5 if we take the beta of the portfolio, that's actually going to be a negative beta, not 0. But there must be some arbitrage trade that we could carry out, right? We have two well-diversified portfolios. They have non-zero alphas. Let's sort of borrow the intuition from our second arbitrage example, and let's actually construct a new portfolio. So let's say we're going to form a new portfolio C, and we're going to do this by combining portfolio A with the risk-free asset F. And we're going to do this such that we actually get a beta equal to the beta of portfolio B. Remember, portfolio A has a high beta of 1.5. Now let's say that we actually want to only put some weight on that portfolio, put the rest in the risk-free asset with 0 beta. How much would we have to put such that the beta of our total portfolio is going to be equal to the beta of portfolio B, or 0.9? Well, the beta of C is essentially going to be W times the beta of A plus 1 minus W times 0, because the beta of the risk-free asset, of course, is 0. So that means that we just want to solve this algebraic equation where W is going to be 0.9 over 1.5, or in other words, 1.5 W is equal to 0.9. And we see that W should equal to 0.6. So we should create this portfolio C that now has 40%, or 1 minus 0.6, in the risk-free asset with an expected return of 5%, and W, or 0.6, in portfolio A that has an expected return that we calculated on the prior slide of 14.5%. Now, what's the expected return on this portfolio? Well, we just multiply this out and we get an expected return of 10.7%. And what is the alpha of portfolio C? Well, we can actually measure it using this CAPM alpha approach, right? We've got our actual return that we expect of 10.7%. We've got our model implied return of our risk-free rate of 5%, the beta of asset A, or sorry, beta of asset C, which is now 0.9, and the risk premium is again the difference between the market expected return of 12% and the risk-free rate of 5%. So now we see that this asset still has a negative alpha of 0.6. Now, what is the alpha of now a long-short portfolio on B and C instead of B and A? This is going to be an actual arbitrage trade, right? Because now we're actually going to have a long-short position in assets with the same beta, and therefore our net beta is actually now going to be 0. So we're going to go long asset B, and we're going to go short asset C, which is, remember, itself made up of 60% of A and 40% of the risk-free rate. And therefore, the beta of this long-short portfolio is going to be 0.9 from B minus 0.9 from C equals 0. And what is the expected return to this? Well, remember, if we go long a share of B, we get our alpha of 2%, and we get our systematic expected return of 0.9 times the expected return to the market portfolio. If we go short one share of C, we get our alpha of C, negative 0.6%. But since we are short it, that negative alpha actually becomes a positive return to our portfolio since we're short a negative number. But it also has a 0.9 beta exposure to the macro risk factor, and that, since we're short, is actually subtracted from our long-short portfolio's exposure, and that's why the two of them actually cancel each other out. Portfolio B has positive 0.9 exposure to the macro factor. Portfolio C has positive 0.9 as well. If we are short C but long B, our net exposure to the macro risk factor is 0. And our expected return is 2.6%. So that is an arbitrage trade again, because again, we've now got no risk in this portfolio. We've eliminated our systematic risk because these are well-diversified portfolios. They have no firm-specific or idiosyncratic risk, therefore there is no more risk at all. But there is a 2.6% expected return. And again, then what would the consequences of this arbitrage trade be? Well, if we're going to go long many shares of B and short many shares of C, which, remember, C is actually going to be 0.6. Each share of C is going to be 0.6 of portfolio A and 0.4 of portfolio F. What that's going to do is it's going to bid up the price of all of the assets in portfolio B and therefore reduce the expected return to all those assets and to portfolio B. And it's going to bid down the price of all of the assets in portfolio A, as well as potentially the risk-free asset, and is going to increase the expected return, and it's going to keep going until the expected return to asset B is going to be equal to the expected return to asset C. At that point, there is no more arbitrage trade because, well, there's no more money to be gained by buying B and selling C if their expected returns are the same. But what then that means is that the return to B is just going to be 0.9 times the return to the market portfolio. The return to asset C is going to be 0.9 times the return to the market portfolio. And therefore, the return to portfolio A is also going to essentially be driven just by its exposure to the macro factor. All of these portfolios must have 0 alpha for there not to be any arbitrage opportunities. In other words, the law of one price must again obtain. Because remember, the law of one price essentially says that if assets have the same economic risk, they should have the same economic expected return. If economic risk is just measured by that single index CAPM beta, well, this means that if assets have the same beta, the way that portfolio B does with portfolio C, their expected returns should be the same, which is just 0.9 times the market expected return net of the risk-free rate. And since portfolio C is made up of the risk-free rate and portfolio A, it means that portfolio A can't have any alpha either. So this is sort of a way of proving the CAPM using no-arbitrage relations, where we can say that the expected return to any well-diversified portfolio is just going to be the expected return, well, I should say the expected return to the portfolio net of the risk-free rate is just going to be the beta of that portfolio times the expected return to the market risk premium. So we're talking about excess returns here. And of course, if we were to simply move the risk-free rate from the left-hand side of the equation over to the right, we could also say that the expected return then to the raw, or the expected raw return of portfolio P for any P is going to be the risk-free rate times, or sorry, plus the beta of that portfolio times the expected return of the market portfolio in excess of the risk-free rate. And that is, of course, the CAPM equation. So this might not be a complete proof. Why? Well, because we've established this for well-diversified portfolios, right? This sort of logic has always been predicated on the idea that there's no firm-specific risk in these portfolios because they're well diversified. That's how we can eliminate all risk and construct these no-arbitrage trades. But at least we've then shown that the security market line from the CAPM does apply to well-diversified portfolios. But does it then also apply to individual risk assets? Because the sort of theoretical equilibrium proof of the CAPM that we made earlier in this discussion, that didn't have that caveat that it must only be well-diversified portfolios. We said that any individual risk asset has that expected return relation that we've now proven using a no-arbitrage argument that we've previously proven using calculus in the equilibrium proof of the CAPM. Well, there's sort of a trick here by which we can actually use the APT insight for well-diversified portfolios to extend to individual risk assets. And it lies in the fact or the realization that individual risk assets make up portfolios. So if we actually do observe the CAPM relation by no arbitrage for well-diversified portfolios, we will say that it must be virtually certain that it holds for most individual risk assets as well. Why do we throw in those two disclaimers, virtually certain and most risk assets? Well, because we can actually still have some individual risk assets that violate the arbitrage pricing theory, but maybe they're not in all portfolios, or they're just a small part of well-diversified portfolios, so they don't actually cause those portfolios to violate the APT relation with the CAPM beta, or at least not very much, but they themselves might actually violate it. But the problem is it can't be more than just a few, because, again, all portfolios are made up of risk assets. So their cumulative deviations can't be such that they would actually cause the portfolios then to deviate themselves. So the APT is essentially sort of a proof of the CAPM for most assets, not just well-diversified portfolios, but most individual risk assets, but perhaps not. So what are some of the differences between the APT and the CAPM? Well, remember, the APT is sort of based on the idea of well-diversified portfolios. But there may be this idea of residual risk, especially for single assets, that doesn't really matter for a well-diversified portfolio. And importantly, the APT actually obtains under much more general assumptions. We don't actually have to have investors care only about mean variance. We don't have to have them all invest in the same portfolio the way that portfolio theory would imply. We don't have to have them have even the same expectations necessarily, though of course they should they should be able to measure betas in the same way in order to construct these arbitrage trades. And the APT can actually be implemented using an observable macroeconomic risk factor. If we're going to use CAPM in APT world, it would be just using the market index, but remember that we can actually have multi-factor versions of the APT, so like the Fama-French model, including the market factor, but also the size factor and the value factor. Those would be sort of observable size and value macro risk factors as well. And of course, the APT actually can tell you when assets are mispriced based on sort of their expected returns relative to their factor exposures. And you can actually then construct trades using it. The CAPM, on the other hand, is based on an unobservable sort of theorized market portfolio, which we proxy for using observable portfolios, but the sort of platonic ideal CAPM market portfolio is actually not observable, because remember, it must include all risky assets, not just equities, but bonds, and not just US equities and bonds, but global, and not just financial assets, but also real assets. So the true market portfolio for the CAPM is actually quite hard to observe. The equilibrium proof, of course, as we saw, was based on mean variance efficiency, and essentially it relies on individuals who can't change prices, who can't actually construct an arbitrage trade that would cause prices to move, but simply construct their holdings in a way that's mutually consistent with each other to create the equilibrium CAPM, expected return to risk relation. But at bottom, both of these paradigms come to that same conclusion, right? That your expected return is going to be just determined by your macro risk exposure. And by macro risk, in the single factor CAPM, we will mean the same thing, or sorry, the single factor APT, we will usually mean the same thing as the market portfolio proxy for the CAPM.